The small piston of a hydraulic lift has an area of 0.3 meters squared. A car weighing 1.5 times 10 to the 4th newtons sits on a rack mounted on the large piston. The large piston has an area of 2.8 meters squared. How large a force must be applied to the small piston to support the car? Alright, let's look and see how we would approach this problem first. You've got a small piston on one side. You've got a larger piston on the other. The area of the small piston is going to be pi r squared, but they give that to you already as 0.3 meters squared in the problem. The car weighing 1.5 times 10 to the 4th newtons sits on the rack mounted on the large piston, so the force, the second force on the larger piston, is 1.5 times 10 to the 4th newtons. Now I left some space here because the force on the small piston is left out and the area of the large piston is left out. So I separate my left side from right side. I call my left side 1. I call my right side 2. Large piston is an area of 2.8 meters squared. So this is 2.8 meters squared. What is the force that must be applied to the small piston in order to lift the car up? The car is on this side. Now, Pascal's principle basically says that the pressure on one side of a hydraulic lift is equal to the pressure on the other side of a hydraulic lift. So the pressure is equally distributed. That doesn't mean that the forces and the areas are equally distributed. If the areas are not the same, then the forces can't be the same either. The general equation for pressure is force over area. So F1 over A1 has to be equal to F2 over A2. We're solving for F1. F1 is going to be equal to F2 A1 over A2. So this is going to give us 1.5 times 10 to the 4th. And A1 is 0.3. A2 is 2.8. So F1 is going to be equal to 1.5 second e to the 4th times 0.3 divided by 2.8. That gives us 1,607.14 newtons. That's F1.